We are Team 2 at UNC Charlotte, and this is our Real-Time Adjusting Traffic System, or RATS for short. Our project focuses on a problem many people deal with every day: traffic that moves way too slowly. When cars stack up, drivers get frustrated, fuel gets wasted, and the whole system becomes less efficient. We set out to improve that by rethinking how traffic lights respond to real conditions on the road. Using an Arduino, our setup detects approaching cars and adjusts the light timing to keep traffic moving as smoothly as possible. It brings together several engineering areas. Civil engineering shapes how the road and pedestrian layout works. Electrical engineering technology handles the sensors and LEDs. Computer engineering brings it all together with code that actually manages the flow. The benefits stack up pretty quickly. Less idling saves fuel, cuts emissions, and reduces time wasted at lights. Cities and local governments would be the ones installing a system like this, but everyday drivers and residents would be the ones who feel the improvements in their routines.
We have been asked to build a small-scale working prototype that could clearly show our engineering solution to a young audience. With these goals in mind and the design specs we were given, we identified 7 key aspects to consider while building the prototype: educational value, interactivity, technical feasibility, durability and accessibility, staying within the budget, appealing to a broad audience, and making sure the design reflected multiple engineering disciplines. Educational value carried the most weight because the science exhibit is aimed towards teaching children something meaningful while keeping them engaged. At the same time, the design needed to be simple enough for our first-year engineering students to build, yet strong enough to hold up to repeated use. Our budget also guided a lot of decisions. We were allowed no more than $50 on new materials and no more than $150 total, including those new materials. We also had to clearly show contributions from at least 3 engineering disciplines, with at least one falling under an EN or ET field. Other important requirements included demonstrating the societal benefits, integrating at least one automated component via microcontroller, and keeping the entire design within an 8 by 10 foot footprint and being no taller than 10 feet.
For the interactive part of the exhibit, we chose movable toy cars because they're fun for kids while still being interesting for older guests. This also encourages guests to experiment with different traffic situations. To meet our budget requirement, we relied mostly on recyclable materials, like cardboard and styrofoam. They're not the toughest materials in the world, but they can hold up well against their environment. They are also easy to cut, shape, and replace if needed. Our automated component uses a sensor to detect incoming traffic and adjust the signal timing. We added a pedestrian indicator as well so that visitors can see when it would be safe to cross, like at a real intersection.
Once we explored a few different ways to tackle the problem, we landed on a solution that made the most sense: adjusting the light timing based on real traffic. To do that, we used sensors to pick up how many cars are approaching and let the system adjust in real time. Along the way, we made a few tweaks that keep the design practical. We first thought about adding a switch that would flip between fixed timer and an adaptive system, but we chose to focus on the adaptive setup since that's the real improvement. We also had to make sure the cars in the demo couldn't be moved or taken, so we added tracks below the road to hold them in place. And instead of building all 4 lanes of the intersection, we narrowed it down since the opposite sides would have shown the same lights anyways. It saves material and lets us use our space more effectively.
As for the actual operating system of our project, we use 2 ultrasonic sensors that collect input that is delivered to our Arduino microcontroller that runs it through a complex algorithm which then produces outputs to one of our 2 LED traffic lights. The way this works is when one sensor detects a vehicle, it turns its respective traffic light green for 5 seconds. Apart from this, after the first car passes, every additional car that passes the traffic light adds 2 seconds to the on duration. This is capped out at 10 seconds to keep the green light from staying on too long. Additionally, if a car remains parked in front of the sensor, it will use the full 10-second duration, which represents heavy traffic. The second function of our operating system is a failsafe that if no inputs are detected for 20 seconds, one of the lights will automatically turn green, which will alternate and revert to a more traditional system. The next feature of our operating system is our pedestrian crossing button. If both lights are red and the button is pressed, it'll turn our pedestrian crossing light green for 5 seconds. Additionally to this, if one of the lights is already green and the button is pressed, it'll cycle that light from yellow to red and then again turn our pedestrian crossing light green for 5 seconds. The final and one of the most simple features of our project is the right-hand turning lane that bypasses the intersection. This will reduce the number of inputs and allow traffic to keep flowing no matter what. If the light is red, the right-hand traffic can continue on as normal.
This project pushed us to think differently by working within a strict budget, with our new materials cost coming out to just over $20 and our reused materials being also a little over $20 as well, bringing our total project cost to $42.80. We also had to work with a limited space and several other requirements which pushed us to improve our coding skills. Looking ahead, there's plenty of room to grow the system. We could expand the setup to show full intersection models or to model complex traffic problems. Extra lanes could be added by adjusting how far the sensor can detect incoming traffic, and we could add a few small changes to improve the pedestrian experience, or even add a timer so that visitors can see actual data that the system runs on. Overall, the project shows how sensors, data processing, and adaptive controls can work together to manage traffic in real time. The results pointing towards a strong potential for improving traffic flow and reducing delays, and they lay a solid foundation for future work in intelligent transportation systems.